Dear students, in the previous classes, you have studied about chemical reaction, thermodynamics of a reaction, chemical equilibrium, free energy change and concentration term. Today, you will learn about rate of a chemical reaction, units of rate of a reaction, average rate and instantaneous rate of the reaction, the effect of the stoichiometry on the rate of reaction. Now, first of all, chemistry by its very nature is concerned with change. Substances with well-defined properties are converted by chemical reactions into other substances with different properties. For any chemical reaction, chemists try to find out the feasibility of a chemical reaction which can be predicted by thermodynamics. As you know that a reaction with delta G less than 0, that is delta G negative at constant temperature and pressure, is feasible. The extent to which a reaction will proceed can be determined from the chemical equilibrium. The speed of a reaction, that is time taken by a reaction to reach equilibrium. Along with the feasibility and the extent, it is equally important to know the rate and the factors controlling the rate of a chemical reaction for its complete understanding. For example, which parameters determine as to how rapidly food gets spoiled? How to design a rapidly setting material for dental filling? Or what controls the rate at which fuel burns in an auto engine? All these questions can be answered by the branch of a chemistry which deals with the study of reaction rates and their mechanisms, called chemical kinetics. The word kinetics is derived from the Greek word kinesis, meaning movement. Chemical kinetics help us to understand how a chemical reaction occurs. Thermodynamics tells only about the feasibility of a reaction, whereas chemical kinetics tells about the rate of a reaction. For example, thermodynamic data indicate that diamond shall convert to graphite, but reality is the conversion rate is so slow that the change is not perceptible at all. Therefore, most people think that diamond is for forever. In this module, we shall be dealing with average and instantaneous rate of the reaction and the factors affecting these. In order to understand all these, let us first learn about the reaction rate. Rate of a chemical reaction. In general, various types of reactions can be categorized in depending upon their rates. First, the very fast reactions. Some reactions such as ionic reactions occur very fast. For example, precipitation of silver chloride occurs instantaneously by mixing aqueous solution of sodium chloride with aqueous solution of silver nitrate. In chemistry lab, in qualitative analysis, reactions are very fast. The reaction is in front of you. Silver nitrate reacts with sodium chloride to give a precipitate of silver chloride and sodium nitrate. The reaction is very fast. Also, the reaction between sodium and water takes place instantaneously to form sodium hydroxide. Combustion reactions and explosive reactions also fall in this category. The rate of such reactions cannot be determined easily. The second type of reactions are very slow reactions. Some reactions are very slow. That is, they require months or even years for completion. For example, rusting of iron in the presence of air and moisture. Fermentation, the process of conversion of sugar to alcohols, and the process of weathering of rocks occurs at extremely slow rate. Rates of such reactions do not possess any significance. The third type, the moderately slow reactions. Also, there are reactions which proceed with a moderate speed. That is, their rate of reaction fall in between the two types mentioned above. The rate for which such a reaction can be measured easily. For example, inversion of cane sugar and hydrolysis of starch. You must be knowing that speed of an automobile is expressed in terms of change in the position or distance covered by it in a certain period of time. Similarly, the speed of a reaction or the rate of a reaction can be defined as the change in the concentration of a reactant or product in unit time. To be more specific, it can be expressed in the terms of the rate of decrease in the concentration of any one of the reactants or the rate of increase in the concentration of any one of the products. Consider a hypothetical reaction assuming that the volume of the system remains constant. R is the reactants converting into P, that is the products. 1 mole of the reactant R produces 1 mole of the product P. If R1, you can see R in the square brackets, that depicts the molar concentration, and P1, or it can be Pi also, just to depict the initial products, are the concentration of R and P respectively at time t1, and R2 and P2 are their concentrations at time t2. Then delta T is equals to T2 minus T1. That symbol delta represents the change. Delta R is equals to R2 minus R1 and delta P is equals to P2 minus P1. The square brackets in the above expression are used to express molar concentration. Now you can see the formula. The rate of the disappearance of R is equals to the decrease in the concentration of R divided by time taken, and it is equals to minus delta R by delta T, or the rate of appearance of P, that is products, is equals to the increase in the concentration of the P divided by time taken. It is equals to delta P upon delta T. The negative sign in the equation 1 indicates the decrease in the concentration of the reactant with the passage of the time. Since delta R is a negative quantity, as concentration of the reactants is decreasing, it is multiplied with minus 1 to make the rate of the reaction a positive quantity. Thus, the rate of reaction is equals to rate of disappearance of R, or it is equals to the rate of appearance of P. You can say minus delta R by delta T equals to delta P upon delta T. And let me tell you, this is a frequently asked question, that what this negative sign or the positive sign in the rate expression depicts. Third is, now the unit of the rate of a reaction. From equation 1 and 2, it is clear that the units of the rate are concentration by time. For example, if concentration is in moles per liter and time is in seconds, then the units will be moles per liter per second. However, in the gaseous reactions, when the concentration of the gases is expressed in the terms of their partial pressures, then the units of the rate will be atmospheres per second. Now let me explain the average rate and instantaneous rate of the reaction. Equation 1 and 2 given represent the average rate of a reaction. R with the subscript AV, that is average rate of reaction, is defined as the change in the concentration of the reactants or the products per unit time taken for that change to occur. I have explained you earlier, that is the change in the concentration in the given time divided by the time taken is equals to minus delta R by delta T is equals to delta P upon delta T. From the graphs you can see, the first one is showing the decrease in the concentration of the reactants with the passage of the time, that is with the increase in the time. The second graph shows you the curve which shows there is increase in the concentration of the products with time. Now, average and instantaneous rate of a reaction. Now, I am taking an example from the concentration of butyl chloride, that is C4H9Cl at different times given below. Calculate the average rate of the reaction. Now, the reaction is given in front of you and we have to calculate the average rate. C4H9Cl plus H2O gives C4H9OH plus HCl. During different intervals of time, the data has been given. We can determine the difference in the concentration of butyl chloride in the different intervals of time, and thus determine the average rate by dividing delta R by delta T. Now, the table 1 shows the average rate of hydrolysis of butyl chloride. The values are in front of you. It can be seen from the table that the average rate falls from 1.90 into 10 raised to power minus 4 moles per liter per second to 0.4 into 10 raised to power minus 4 moles per liter per second. However, average rate cannot be used to predict the rate of a reaction at a particular instant, as it would be constant for the time interval for which it is calculated. So, to express the rate at a particular moment of the time, we determine the instantaneous rate. It is obtained when we consider the average rate at the smallest time interval, say small d t. Now, instead of delta, we are using small d. Delta represents average change, small d represents infinitesimally or a very small change. That is when delta t approaches 0. Hence, the instantaneous rate of the reaction can be defined as the decrease in the concentration of any one of the reactant or increase in any one of the product at a particular instant of time. Thus, mathematically, for an infinitesimally small time interval, that is dt, instantaneous rate is given by R average is equals to minus delta R by delta T equals to delta P upon delta T, and as delta T approaches 0, R instantaneous is equals to minus dr by dt is equals to dp by dt. It can be determined graphically by drawing a tangent at time t on either of the curves for concentration of R and P versus time t and calculating its slope. So, in the previous problem, R instantaneous at 600 seconds, for example, can be calculated by plotting concentration of the butyl chloride as a function of time. A tangent is drawn that touches the curve at t is equals to 600 seconds. From the graph, you can see the plot and the tangent. Instantaneous rate of the hydrolysis of the butyl chloride is shown in the figure. The slope of this tangent gives the instantaneous rate. So, our instantaneous at 600 seconds is equals to minus 0.0165 minus 0.037 divided by 800 minus 400 seconds moles per liter. It comes out to be 5.12 into 10 raised to power minus 5 moles per liter per second. At time t equals to 250 seconds, the R instantaneous equals to 1.22 into 10 raised to power 4 moles per liter per second. And at time t equals to 350 seconds, R instantaneous is equals to 1.0 into 10 raised to power minus 4 moles per liter per second. Now, the effect of the stoichiometry on the rate of the reaction. Now, consider a reaction mercury Hg plus Cl2 gives HgCl2, where stoichiometric coefficients of the reactants and the products are same. Then rate of the reaction is given as the rate of reaction equals to minus delta molar concentration of Hg divided by delta T. It is equals to minus delta molar concentration of Cl2 divided by delta T, which is further equals to delta molar concentration of HgCl2 upon delta T. That is, the rate of disappearance of any of the reactants is same as the rate of appearance of the products. But in the following reaction, 2 moles of Hi decompose to produce 1 mole each of hydrogen and iodine. The reaction is 2Hi gives H2 plus I2. For expressing the rate of such a reaction, where stoichiometric coefficients of the reactants or the products are not equal to 1, the rate of disappearance of any of the reactants or the rate of appearance of the products is divided by their respective stoichiometric coefficients. Since the rate of consumption of hydrogen iodide is twice the rate of formation of hydrogen or iodine, to make them equal, the term delta molar concentration of Hi is divided by 2. The rate of this reaction is given by, the rate of reaction is equals to minus 1 by 2 delta Hi by delta T equals to delta H2 by delta T equals to delta I2 by delta T. Similarly, for the reaction 5 bromide ion plus bromate ions BrO3 minus 1 plus 6 H ions gives 3 Br2 plus 3 H2O. For such reaction, the rate of a reaction is equals to minus 1 by 5 delta molar concentration of the bromide ions divided by delta T. It is equals to minus delta molar concentration of the bromate ions divided by delta T. It is equals to minus 1 by 6 delta H ions by delta T, which is further equals to 1 by 3 delta molar concentration of bromine divided by delta T. It is equals to 1 by 3 delta molar concentration of water by delta T. All these expressions shows you the negative sign before the reactants and the positive sign before the products. For a gaseous reaction at constant temperature, concentration is directly proportional to the partial pressure of the species, and hence the rate can also be expressed as a rate of change in the partial pressure of the reactants or the product. I am taking another example. The decomposition of N2O5 in carbon tetrachloride at 318 Kelvin has been studied by monitoring the concentration of N2O5 in the solution. Initially, the concentration of N2O5 is 2.33 moles per liter, and after 184 minutes, it is reduced to 2.08 moles per liter. The reaction takes place according to the equation. 2 N2O5 in the gaseous state gives 4 NO2 gaseous state plus oxygen again in the gaseous state. Calculate the average rate of this reaction in terms of the hours, minutes and seconds. What is the rate of the production of NO2 during this period? Now the solution, average rate of reaction, it is equals to half minus delta molar concentration of N2O5 divided by delta T. Now putting the values, minus half 2.08 minus 2.33 moles per liter divided by 184 minutes. After calculating, it comes out to be 6.79 into 10 raised to power minus 4 moles per liter per minute. It is equals to 6.79 into 10 raised to power minus 4 moles per liter per minute into 60 minutes per hour equals to 4.07 into 10 raised to power minus 2 moles per liter per hour. Now, 6.79 into 10 raised to power minus 4 moles per liter per minute into 1 minute by 60 seconds. It is equals to 1.13 into 10 raised to power minus 5 moles per liter per second. Also, average rate of reaction is equals to half minus delta molar concentration of N2O5 divided by delta T equals to 1 by 4 delta molar concentration of NO2 divided by delta T is equals to 6.79 into 10 raised to power minus 4 moles per liter per minute. Hence, rate of production of NO2 equals to delta NO2 by delta T is equals to 6.79 into 10 raised to power minus 4 into 4 moles per liter per minute, and it comes out to be 2.72 into 10 raised to power minus 3 moles per liter per minute. Another example, for the reaction R depicts the reactants, gives the products, that is P. The concentration of the reactant changes from 0.03 molar to 0.02 molar in 25 minutes. Calculate the average rate of the reaction using units of time both in minutes and seconds. Now the solution is, the average rate of the reaction R giving the products equals to minus delta R by delta T. It is equals to minus R2 minus R1 by T2 minus T1. Now we know that molar concentration of R2 is equals to 0.02 molar, whereas concentration R1 is equals to 0.03 molar and delta T is equals to 25 minutes. Therefore, average rate is equals to minus 0.02 minus 0.03 divided by 25 molar per minute. It comes out to be minus 0.01 by 25 molar per minute. It is equals to 4 into 10 raised to power minus 4 molar per minute. It is equals to minus 0.01 divided by 25 into 60 molar per second. So the answer in seconds will be 6.66 into 10 raised to power minus 6 molar per second. Another example, in a reaction 2A giving the products, the concentration of A decreases from 0.5 moles per liter to 0.4 moles per liter in 10 minutes. Calculate the rate during this interval. Again the solution, the average rate of the reaction 2A giving the products will be, it is equals to minus half delta molar concentration of A divided by delta T equals to minus half A2 minus A1 divided by T2 minus T1. Now A2 is 0.4 moles per liter, A1 is 0.5 moles per liter and delta T is 10 minutes. So after putting the values, the average rate is equals to minus half 0.4 minus 0.5 divided by 10 moles per liter per minute. It comes out to be minus half into minus 0.1 by 10 moles per liter per minute. Final answer is 5 into 10 raised to power minus 3 moles per liter per minute. Another example, in a hypothetical chemical reaction 2A giving 4 moles of B plus 1 mole of C, the concentration of B is found to increase by 4 into 10 raised to power minus 4 moles per liter in 10 seconds. Calculate A, the rate of appearance of B. Second part, the rate of reaction, and the third is the rate of disappearance of A. The solution, for the reaction 2 moles of A giving 4 moles of B plus 1 mole of C. First of all, let us calculate the average rate of reaction. 1 by 4 into rate of appearance of B, it is equals to 1 by 4 delta molar concentration of B divided by delta T. It is equals to half into rate of disappearance of A. It is further equals to minus half delta molar concentration of A by delta T. Part A, the rate of appearance of B is equals to increase in the concentration of B divided by time taken. It is equals to 4 into 10 raised to power minus 4 divided by 10 moles per liter per second. It is equals to 4 into 10 raised to power minus 5 moles per liter per second. B, rate of reaction is equals to 1 by 4 into rate of appearance of B. It is equals to 4 into 10 raised to power minus 5 divided by 4 moles per liter per second. It comes out to be 1 into 10 raised to power minus 5 moles per liter per second. Next part, the rate of disappearance of A. It is equals to 2 into rate of reaction. It is equals to 2 into 1 into 10 raised to power minus 5 moles per liter per second. It is equals to 2 into 10 raised to power minus 5 moles per liter per second. Now again another example. In a chemical reaction, the iodide ions are oxidized by peroxy disulfate ions. The reaction goes like this: 3I minus plus S2O8 minus gives I3 minus plus 2SO4 2 minus. If the rate of disappearance of peroxy disulfate ions is 3.5 into 10 raised to power minus 4 moles per liter per second for a given interval of time, then calculate the rate of disappearance of iodide ions for the same time interval. Also calculate the rate of formation of sulfate ions for the same time period. The solution: for the given reaction, average rate of reaction is equals to minus 1 by 3 delta molar concentration of iodide ion divided by delta T. It is equals to minus delta concentration of peroxy disulfate ions divided by delta T. It is equals to delta molar concentration of I3 negative ions divided by delta T. It is equals to half delta molar concentration of the sulfate ions by delta T. Given the rate of disappearance of peroxy disulfate ions is equal to minus delta the molar concentration of S2O8 2 minus ions divided by delta T equals to 3.5 into 10 raised to power minus 4 moles per liter per second. Therefore, the rate of disappearance of iodide ions minus delta iodide ion by delta T, it equals to 3 into minus delta molar concentration of S2O8 2 minus ions divided by delta T. It comes out to be 3 into 3.5 into 10 raised to power minus 4 moles per liter per second. It is equals to 10.5 into 10 raised to power minus 4 moles per liter per second. Also, the rate of formation of the sulfate ions, delta molar concentration of the sulfate ions divided by delta T is equal to 2 into minus molar concentration of the peroxy disulfate ions by delta T. After putting the values, it is equal to 2 into 3.5 into 10 raised to power minus 4 moles per liter per second. The final answer is 7.0 into 10 raised to power minus 4 moles per liter per second. Now let me summarize what we have studied today. Chemical kinetics is the study of the chemical reactions with respect to the reaction rates. This module described various chemical reactions associated with different types of reaction rates. The rate of a reaction is concerned with decrease in the concentration of the reactants or increase in the concentration of the products per unit time. The rate of the reaction can be expressed as either instantaneous rate or average rate. Average rate of the reaction is defined as either the decrease in the concentration of any one of the reactants or increase in any one of the products over a large interval of time. On the other hand, the instantaneous rate of the reaction is expressed as either decrease in the concentration of any one of the reactants or increase in any one of the products at a particular instant of time. Average rate is expressed as minus delta molar concentration of the reactants by delta T equals to delta the molar concentration of the products by delta T, and instantaneous rate is expressed as minus delta molar concentration of R by delta T equals to D molar concentration of the products by delta T. The rate of the reaction is generally expressed in the units of concentration per time. For example, moles per liter per second or moles per liter per minute or moles per liter per hour. However, in the gaseous reactions, when the concentration of the gases is expressed in terms of their partial pressures, then the units of the rate equation will be atmospheres per second. There are number of factors that affect the rate of the reaction, which will be discussed in the next module. So dear students, I hope the average rate and the instantaneous rate concept will be clear to you, and how to calculate simple numericals based on the formula. And also it is very significant to put the negative sign before the reactants and the positive sign before the products. I hope everything is very clear to you. Thank you.